Okay, so I just want to finish off the chapter here, so it shouldn't take too long. I just want to talk about the experiment. Most of you did a really, really good job on this, so you know what you're doing, which is great. Measuring the volume of liquid. So when we're measuring the volume of liquid in a lab, generally speaking, you use a graduated cylinder. Okay, and that's, you can get different sized ones and they have little markings up the side, and then you pour the water in and you should be able to measure it to a pretty high degree of accuracy. Measuring the volume of a solid, so if it's a regular solid, what we're looking at for volume here is length multiplied by width multiplied by height. Okay, so it's just 3 measurements using a meter stick. The third one here then was measuring the volume of irregular solids. So I suggested a small stone and a large stone as our irregular solids. So a small stone would fit in a graduated cylinder. So what you do is you put in your graduated cylinder and you put some water into it. I don't know, let's say 50 mils of water. And then in the top you drop in the stone, and that will cause the water to go up, let's say to 60 mils. Whatever it went up by is the volume of the stone. Okay, milliliters and centimeters cubed are the same thing. So generally speaking, it's milliliters when it's liquid and centimeters cubed when it's solid. Okay, so the difference between the two. Now, the large stone won't fit in the graduated cylinder, which is where you get a problem. You create a problem, I suppose. But what we do in that case is we use our overflow can, which again I know from your experiments most of you figured out. So you put the water into the overflow can and you fill it right up to the top. You actually fill it over the top and allow it to flow out until it's exactly at the top. And then underneath the spout you put in a beaker, and in here you drop in the large stone. And what happens is that causes the water to rise and the water flows off into your beaker, and then from there you can get the volume. So the volume of water that this stone displaces or moves is equal to the volume of the stone itself. Okay, so that was just a quick explanation. So all that's left in this chapter is, where am I? Here. Is accuracy, errors, taking measurements, okay? And something that's incredibly important in physics is that, I mean, it's important in all aspects of science, I suppose, but there's a huge amount of measurement in physics and it has to be done accurately. So it's really, really important that you do that. And if you don't measure the things you're trying to measure in a correct and accurate way, then you end up with like crazy answers. So we do experiments in Leaving Cert physics to measure acceleration due to gravity, and the key here is we know the answer. So we know what the answer should be, and if you don't take your measurements correctly, then you won't get that answer. So down here, the important part down here, there are 2 main sources of error when taking measurements: random errors and systematic errors. Okay, so that you need that in your notes. Oh, I hate this book. Sorry, I absolutely hate this book. Right. Oh my god. I'm trying to not lose the head. Right. Okay. Random errors cause specific readings to be too high or too low. So random errors are exactly that, they're random. So sometimes, or most of the time, it's human error. It's where you measure 8 of the readings perfectly, and then in the 9th one, you make a mistake. You make a stupid mistake. And it tends to look wrong. It's way out. You can see this, the bee over here in the graph. See this here? Like it tends to be way off what everything, all your other things are. So there's random errors cause specific readings to be too high and too low. So here's one that's too low, and here's one here that's too high. So yeah, generally speaking, it will affect one, maybe two readings. And that is part of the reason why it's incredibly important that we do an average. So an average will, it won't completely remove your error, but it will definitely help to minimize your error. And so as I was saying here, a random error will stand out as an outlier. So it'll, all your data will be lovely, and you'll have one random one, and you'll be like, oh God, I must have made a mistake there. I'll go back and have a look. A lot of the time, again, in Leaving Cert Physics, we would do the data, and like I was saying, gravity is 9.8. We'll get like 9.7, 9.9, 9.8, 9.85, and get like 11.2. You can clearly see you did something wrong there, so you can go back and try it again or see where your error was. Okay, so for your notes, you need the first line there that's underlined. To avoid random errors, an average of the data is taken, and when compared to the rest, a random error will stand as an outlier. Those three sentences need to go into your notes. Okay. The other type of error tend to pose a different problem because they don't stand out as easily. Systematic errors. So they cause all readings to be wrong. And sometimes it's down to the person. They don't. They have taken up how to do it wrong. Okay, so they took the teacher's instructions. They set out to do it, but they're doing it wrong repeatedly. And that's one reason for it. The other reason for it is something like this. See here? So you have a meter stick and it's worn away here at the edges. So it doesn't go to zero. That corner there has been kind of taken off. So your readings are all going to be off by like a mil, maybe 2 mils. And this here, we talked about this a couple of weeks ago, Newton spring balance. And before you use these, you have to like wind them to get them back to zero, because you can see here the red line is not at zero, and as a result, all of your readings will be off. Okay, so that's the difference between a random error